Welcome to our quantum deep dives.
Hello.
Today, we're diving headfirst into the really fascinating world of the Penning trap.
Right.
And we're basing this on a great essay by Jargo Schneeppert called Penningfälle, Precise Teilchenkontrolle in der Quantentechnologie.
Yeah, it's a really insightful piece. And at its core, what Schneeppert explains is that the Penning trap is this special setup.
Right.
It uses electric and magnetic fields together very cleverly to hold on to charged particles, things like ions or electrons.
So it grabs them and just holds them there.
Pretty much, yeah, for surprisingly long times.
Yeah.
Think of it as a super, super precise container for, the tiniest bits of matter.
Exactly. And Schneeppert really emphasizes how this precise control works. It's a strong magnetic field, right, that stops the particle moving sideways.
That's the idea. It confines it in one plane, and then there's an electric quadrupole field.
Okay, and what does that do?
That one contains it along the axis, sort of stops it drifting out the ends. It's really quite ingenious physics.
It really is.
Yeah.
And we'll dig into the physics behind it, drawing on Schneeppert's work, of course.
And maybe touch on the history, too. Goes back to the Dutch physicist Franz Michel Penning in the 1930s.
Right. He sort of laid the groundwork.
Yeah.
Then Hans-Georg Demelt, in the 50s, he really developed it further.
He did significant advancements. And that work, as Schneeppert notes, eventually led to a Nobel Prize for Demelt for his work on ion traps generally.
Wow. So it shows how these ideas build over time.
Absolutely. And, Schneeppert points out why they wanted this device in the first place. The goal was this incredibly controlled environment.
To study particles really close.
Exactly. With unprecedented precision. That was crucial for nailing down fundamental physical constants.
Okay.
And for, getting our first real look at antimatter and just developing totally new measurement techniques.
Okay, so let's get into the nuts and bolts a bit more. Schneeppert's essay, it really stresses the interaction between the charged particles and these fields, right?
Yes, that's the absolute key. The interplay between the electric and magnetic fields is what allows us to, control and stabilize how the particle moves.
And there's a specific frequency involved.
Right. Schneeppert introduces the concept of the cyclotron frequency. There's a neat little equation for it, XQBM.
Okay, let's break that down. X is the frequency.
The cyclotron frequency, yeah.
Yeah.
Q is the particle's charge, B is the magnetic field strength, and M is the mass.
So what does that equation actually tell us? What's the takeaway?
Well, what's really neat, and Schneeppert explains this well, is how directly it links these properties. If you crank up the magnetic field, B, or if the particle has more charge Q, it spins faster.
Okay.
But if the particle is heavier, M, it spins slower. It's like a fingerprint for the particle in that specific field.
Interesting. Now, Schneeppert mentions Penning's early work in the 30s. What was he actually doing back then?
Well, Schneeppert explains that Penning was mainly looking at how charged particles moved around in gas discharges. So not quite the trap we know today.
Okay. More foundational stuff.
Yeah, foundational. His experiments, though, manipulating and watching these particles, gave those crucial early insights into how they react to electromagnetic forces.
Got it. And then Demelt, you said the 1950s. What was his specific contribution?
So as Schneeppert details it, Demelt took Penning's basic ideas and really refined the technology. He had a very specific aim.
Which was?
To investigate the fundamental properties of individual particles. He wanted that super controlled environment we mentioned, but with the precision needed to really pin down those fundamental constants.
Right, that extreme precision.
Exactly.
So Schneeppert then moves on to how significant the Penning trap is today in modern physics and quantum tech. It sounds like it's used all over the place.
Oh, absolutely. Schneeppert makes it clear this isn't just some obscure lab device. It's become, essential. Mass spectrometry, antimatter research, quantum technology.
Let's take mass spectrometry first. How does the trap help there?
The key thing, Schneeppert points out, is holding on to ions for a long time. This lets scientists measure their mass with just incredible accuracy.
How accurate are we talking?
Extremely. It's used to get really precise masses for protons, neutrons, even antiprotons. It's a cornerstone of high-precision mass spec.
And antimatter. That always sounds like sci-fi. How are Penning traps used at places like CERN?
Well, Schneeppert highlights that places like CERN absolutely rely on Penning traps. They use them to actually capture and hold antiprotons.
So you can actually bottle up antimatter.
In a way, yes. Once trapped, scientists can study its properties, and this is vital for testing fundamental symmetries, like the CBT theorem.
CPT.
Yeah, it basically suggests a deep symmetry between matter and antimatter. And Schneppat mentions the ALPHA collaboration using these traps to make antihydrogen, which is just amazing.
Wow, okay, now shifting to quantum computing, that's a huge buzzword. How does the Penning trap fit in?
This is where it gets really exciting, I think. Schneppat explains that ion traps in general, and Penning traps are a great example, are used to store and, crucially, manipulate individual charged particles.
As qubits.
Exactly. The amazing control these traps offer lets scientists precisely manage the quantum states of these ions. That makes them really promising candidates for qubits in future quantum computers, and also for quantum metrology super-sensitive measurements.
And Schneppat also mentioned fundamental tests of physics.
Yes, he underscores how Penning traps have enabled some of the most precise tests of the standard model we have.
Like what, for example?
The classic example Schneppat gives is measuring the electron's magnetic moment. Using Penning traps, they've measured it with an accuracy that's just mind-boggling, like parts per trillion, 12 decimal places or more.
That's insane precision.
It really is, and it provides incredibly tough tests for our fundamental theories.
Okay, let's dive a bit deeper into the physics again. Schneppat reminds us about the Lorentz force governing the motion. That's fundamental, right? F equals QE plus VXB.
Absolutely fundamental. As Schneppat states, that equation tells you exactly how a charged particle Q moving with velocity V will react to an electric field and a magnetic field B. It's the rulebook for its motion.
And if you just had a uniform magnetic field, what happens then?
In that simple case, Schneppat describes how the magnetic part of the force, QVXB, pushes the particle sideways, perpendicular to both its motion and the field.
Making it go in circles.
Exactly. That's the cyclotron motion we talked about with that specific cyclotron frequency.
But the Penning trap isn't just a magnetic field. There's that electric quadrupole field, too. What's its role again?
Right. Schneppat clarifies that the magnetic field alone traps it radially, but doesn't stop it zipping along the field lines. The electric quadrupole field adds a specific electric potential.
Framed like a saddle.
Sort of, yeah. It creates a potential well along the axis. It gently pushes particles back towards the center if they try to drift along the axis. That gives you stable axial confinement.
So combine the magnetic confinement of the plane and the electric confinement along the axis. What's the overall motion like?
Schneppat explains it results in this characteristic, stable, triple motion. You've got the fast cyclotron whirl. Then there's a slower drift around the trap center called the magnetron motion, which comes from the interplay of E and B fields.
Okay.
And finally, there's the axial oscillation, the particle bouncing back and forth along the trap's axis because of the electric field. It's the precise dance of these three motions that keeps it trapped.
Right. So Schneppat then discusses actually building one of these. Sounds complicated.
Oh, it is. As Schneppat outlines, it's pretty sophisticated engineering. You need a really strong, really stable magnetic field, often from superconducting magnets.
Which need to be super cold.
Exactly. Cryogenic temperatures. Yeah. And then you need that precisely shaped electric quadrupole field.
How's that electric field made?
Schneppat details the usual setup. 3 electrodes, a central ring electrode, and then 2 end cap electrodes, one on each side along the axis.
You apply voltages to those?
Yep.
Applying the right voltages creates that specific potential shape, the one often described by that polynomial equation, A xyz equal times ein Zanus x off plus y2 over d Wetterall.
Schneppat also says there are different types of Penning traps.
That's right. He notes that while the classic design is fundamental, people have developed variations. There are miniaturized ones, which could be huge for portable applications. And things like multipolar Penning traps, including specialized ones like MALDI Penning traps used in mass spectrometry for big molecules.
And how do you actually get the particles in there and keep them for weeks or months, you said?
Yeah, Schneppat describes it as a multi-step process. First, you generate or inject the particles. Then, crucially, you need to cool them down.
Why cool them?
To reduce their energy so they stay trapped and you can measure them precisely. Techniques like laser cooling or resistive cooling are common.
Okay.
And finally, you need an incredible vacuum. Ultra-high vacuum, like 10 Joule millibar or even better, down to 10 Joule. That minimizes collisions with stray gas atoms, allowing those really long storage times. Right, that makes sense. Now, Schneppat really digs into the quantum technology applications. It's clearly a big deal there.
A very big deal. As Schneppat highlights, that precision we keep talking about makes them indispensable for a whole range of quantum tech tasks. especially high-precision measurements.
What kind of measurements exactly?
Schneepat emphasizes determining charge-to-mass ratios with extreme accuracy. By measuring that cyclotron frequency in a known B field, you can calculate QM incredibly precisely. That pins down particle masses.
Like protons and antiprotons.
Exactly. And he also mentions measuring their magnetic moments like tiny compass needles with that astonishing 10 UA precision. Huge for understanding antimatter.
And what about quantum computing and simulation? You mentioned qubits earlier.
Right. Schneepat explains, penning traps are great platforms for holding and manipulating individual ions as qubits. You get amazing control using lasers, stable fields.
So you can prepare specific quantum states?
Precisely. Prepare them, manipulate them, read them out. He even mentions tracking chains of ions to perform multi-qubit gate operations. That's a key step towards building useful quantum computers.
And finally, spectroscopy and metrology. What's the penning trap's role there, according to Schneepat?
Schneepat underscores its use for super precise frequency measurements. These are vital for nailing down fundamental constants like the proton-to-electron mass ratio, and for studying the fine details of atomic energy levels. He brings up that electron G-factor measurement, again, relative accuracy of 10 Uris, as a landmark achieved using penning traps.
And this impacts our measurement standards.
Directly. Schneepat points out these ultra-precise measurements contribute to redefining fundamental SI units, like the kilogram, so it affects the very foundation of how we measure things.
Now, Schneepat compares the penning trap to the Paul trap. What's the main difference he draws?
The core difference, as Schneepat explains, is how they trap. Paul traps use rapidly oscillating electric fields. Penning traps use static magnetic and electric fields.
Okay, static versus oscillating.
Right, and that fundamental difference gives them different pros and cons.
Such as? What advantages does Schneepat point out for each?
Well, he notes penning traps generally offer higher precision and much longer storage times. That's key for those ultra-sensitive measurements. But they need those big, strong magnets.
Which are complex.
Right. Paul traps, on the other hand, are often simpler to build, maybe more flexible for some things. But their precision can be limited by something called micromotion caused by the oscillating field, and storage times aren't usually as long.
And Schneepat mentions hybrid traps briefly. What's the aim there?
The idea, as Schneepat puts it, is basically trying to combine the best features of both. Maybe you get high precision and flexibility, or better scalability. It's an active area of research.
Finally, Schneepat looks ahead. Challenges and the future. What are the main hurdles?
He highlights a few key things. Those extreme vacuum requirements are tough. Maintaining incredibly stable fields is a constant challenge. And then there's the difficulty of miniaturization and integrating these traps effectively into larger, scalable quantum systems.
And looking forward, what possibilities does Schneepat see?
He seems quite optimistic. For quantum computing, he talks about using multiple ions in shared traps, building coupled quantum registers.
Yeah.
In fundamental physics, he suggests future experiments could measure things like electric dipole moments, refine constants even further, maybe even directly test gravity's effect on antimatter.
Wow. Testing antimatter gravity.
Yeah, a huge goal. And he also sees continued contributions to metrology, even better frequency standards, refining those SI units further.
So the penning trap, as Yurgo Schneepat's essay really brings home, it's just a remarkable piece of ingenuity, isn't it? Our quest to understand and, well, control the universe's building blocks.
It truly is. From those early gas discharge studies Schneepat mentions, right up to being absolutely vital in today's quantum tech. It's become indispensable.
And that incredible precision, as Schneepat shows, it hasn't just let us test fundamental physics theories really rigorously.
No, it's actively paving the way now for revolutions in computing, in sensing, and, our basic understanding of matter versus antimatter.
Yeah. And as Yurgo Schneepat's essay suggests, the challenges, like scaling and miniaturization, they're definitely significant.
Oh, for sure. They're big hurdles. But the potential payoff is just immense. The future of quantum tech, fundamental physics. It seems clear that penning traps and innovations based on them will be a big part of the story.
Well, thank you for joining us on this quantum deep dive into the world of the penning trap, all guided by the excellent work of Yurgo Schneepat.
Hope it was interesting.
We certainly hope this has sparked your curiosity and given you a deeper appreciation for this really crucial piece of technology.